Hello, Ridwan. It's going well. It's going well. How are you? Yeah, we all are. We all are. We are halfway through. Almost. Uh, I mean, it definitely feels like more work than I usually would when I'm in the office. I don't know if that's just because that everything is online, like there's more coordination to do, or technology sometimes fails us, like it did on the very first lecture when e-class was down and everything like went downhill. um, I just feel it's more challenging now. So, and I can only imagine with like being a student and having 4 or 5 courses, and especially if you're in a different time zone. Like some of the courses I'm teaching or some of the courses I'm involved with span 5, 6 time zones, not just within like North America, but like some people across the world. Some people are in Asia, some people are in Europe, some people are in North America, some people are some other conferences that I'm co-organizing. Like it's even more challenging because there you have to balance your audience. So your audience would come from like Australia, New Zealand, and also Canada, the US, and Europe, and India, and China, and everywhere. Like how do you do that? It takes a significant amount of time and effort just to be able to come up with a program for the conference, just to be able to be fair to everyone. Everyone is trying their best. Everyone is doing their best now. All right. I guess most of us are here. Hi everyone. It's good to have you all before this long weekend. Before I begin the lecture, I just have something to talk about now that grad school applications are about to be open, both in Canada and the US at least. So one thing that I would like to bring to your attention is the NSERC deadline for master's students. That is, if you want to start your master's degree a year from now, you would have to apply now so that you can start in fall 2021. And the deadline for master's students to submit their applications is December 1st, 2020, so in less than 2 months from today. And in our department, my colleague, Dr. Saranadi, has started an initiative, I think last year, to help students who are applying both for NSERC Masters or PhD to go with them over their material and work and research statement and so on, so that we can improve the chances of students from our department applying to those prestigious awards. So who is eligible for NSERC? It is for Canadians and permanent residents only. You need to have a GPA that is at least 3.5 in the last 2 years of your study. So just compute your GPA for the last 2 years, see if it's 3.5 or above. And you have to be joining a research-based program, which means that you cannot get NSERC if you want to do a course-based master's. Why would you apply for NSERC? Well, you're gonna get more than 17K for 1 year. That's a decent amount of money. It's a very prestigious scholarship on your CV that if you get it, it will help you get more scholarships along the way. And there is a higher chance of getting into a university that you want. You can choose up to 3 universities or 3 institutions where you can, in your application, to say that I'm gonna take my award and work at this university or that university and this university. So why would it increase your chances? Because it means that you have some guaranteed funding for at least 1 year. So you'll be a good candidate for professors looking for master students. You can work with your intended supervisor even if they don't have full funding, because you're basically sparing them of 1 year of funding, and that means a lot for professors when they are planning their financial situation. Specifically for the U of A, why would you consider getting your NSERC and at the U of A and listing the U of A as one of your universities? There is a wide range of opportunities for research, from AI, machine learning, software engineering, programming languages, compilers, high performance computing, robotics, you name it, you'll find it in our department. And at the U of A, which is unique to our department, you get an automatic top-up of $5,800. So that is on top of whatever you're going to get from NSERC, as a recognition of how prestigious this award is. So how would the department help? There is an FGSR info session on October 27th. You must have gotten an email about it, and if you haven't, please reach out to me and I'll forward that email to you. There is also a short link there on the top left for more information about it, and there is the QR code that you can just scan now and go to the website. Like I said, my colleague Dr. Saraneri is going to have individual review appointments for your application materials between November 16th and November 25th. So that gives you like 5 weeks roughly of preparation, or maybe even 6 weeks of preparation before those individual appointments. I do strongly encourage you that if you are considering grad school, to apply for NSERC if you are eligible, and if you are, work hard to have your application material before that week of individual review appointments, and make sure you sign up for one and seek help from an experienced professor like Dr. Nadi. If you also have any questions about grad school in general, or NSERC opportunities, or maybe other potential funding opportunities, feel free to reach out to me. I'll be happy to talk about it with you at any point. Make sure that we find some time that is suitable to you so that we can discuss that. Do you have any questions about this? All right. If you do, anyways, like I said, just reach out, email me. I'll be happy to answer any questions if I know, or if I don't, I'll direct you to the person that knows the answer to those questions. Having said that, let's continue with our discussion from Tuesday. And in today's lecture, we are going to talk about another framework. This is actually one of my favorite lectures in the course. My most favorite lecture is lattice theory with all its components, and this comes close to my best or most favorite lecture, or maybe my second favorite lecture after lattice theory, just because lattice theory is kind of the cornerstone for everything that we're doing in program analysis, really. So it's going to be about IFDS framework. So let's have a quick refresher about what we discussed in the previous lectures. In the previous lecture, we talked about context sensitivity and how context sensitivity allows us to eliminate some of those invalid paths in a program and focus only on propagating data flow facts along valid paths in the program. And there are various ways you can do context sensitivity. There are the naive ways like method cloning or method inlining, but those may not help the analysis scale up to large code bases. So the other two techniques that are commonly used, or in practice they are commonly used, is the call strings approach, where instead of propagating data flow facts on their own, you propagate a pair of a data flow fact associated with the call string that represents the call stack up to that point. Every time you call a method, you append that method onto the call stack. Every time you return from the method, you remove a message from the call stack, and that way you ensure that you remember your way or the path that got you to that point in the program. On the other hand, this might not be a useful approach if you have multiple repeated calls to the same method over the whole program. because at every single time you analyze the same method, you're going to redo the same work again and redo the computations again and again over that method. So this is where the functional approach shines here. You just analyze the method once, you create a summary for it, and that summary can be reused and parameterized depending on the calling context at that point. And this is where actually IFDS leverages this technique to make its framework, or to make the IFDS framework reusable and beneficial and useful to many, to solve many analysis problems. So in today's lecture, we're going to talk about IFDS, Interprocedural Finite Distributive Subset Problems. And this work was first introduced by Tom Reps, Susan Horwitz, and Muli Sagiv back in 1995. It was published at POPL. I strongly encourage you to read that paper. It's one of the classical papers in program analysis. There is a subsequent paper about an abstraction over that framework called IDE, or Interprocedural Distributive Environments, that I will allude to at the very end of our lecture, and maybe have time to talk about it more in our next lecture, depending on how today's lecture will go. So, Interprocedural Finite Distributive Subset Problems. This is why we call it IFDS. This is what it stands for. I kind of like to think about IFDS as the interprocedural counterpart of the monotone framework. If you remember from our lectures in the beginning of the course, the monotone framework is a framework that allows you to have a single algorithm to solve program analyses, or to solve analysis queries, that is configurable enough that you can describe and define various types of analyses using kind of the same algorithm. But it works intra-procedurally within the same method. IFDS offers kind of the similar features, but inter-procedurally across method boundaries throughout the whole program. So let's see how that actually is done. Well, interprocedural, from the name, you can tell that it actually reasons about different methods in the same program and not just a single method. So how do we do that? Well, we just learned in the previous two lectures that we can just create the program supergraph, or the interprocedural control flow graph, ICFG of the program. You create the control flow graph of one method, you could create the control flow graph of the other one, and then you connect them at call sites, calls and return, using call and return edges. Finite, here comes again lattice theory, because here the flow functions that we define in our program are all defined on a finite lattice. So you cannot have an infinite lattice for your analysis domain here. All of them are defined using a finite lattice. When we do that, when you associate all the edges across the interprocedural control flow graph, or ICFG, you associate each edge with a flow function that is defined over a finite lattice. We call that graph exploded supergraph. So first you have a control flow graph for a single method. You connect those control flow graphs of various methods, you get ICFG, or the interprocedural control flow graph, or the supergraph. You annotate that ICFG with flow functions, you get an exploded supergraph, or an ESG. And we're going to use those acronyms as we go from now on. So the lattice is finite, that's why it's finite. Distributive, because the flow functions, again recall from our lattice theory classes, distributivity means that it doesn't matter the order of applying the function versus finding the join in the lattice. If you apply the function first and then do the join, it's the same as finding the join of those two elements and then apply the flow function. Both will give you the same thing. This is what distributivity means. And we'll see how that would actually allow us to find a more exact solution to our analysis problem. We actually talked about this during the lattice theory classes and the monotone framework classes. Do you remember what distributivity buys you? If you define all your flow functions as distributive, what does that imply about your solution? There is a significance here for having your flow functions all to be distributive. What was that about? It had to do with the lattice of solutions, if you recall that. So I'm saying your flow functions, if they are all distributive, that has an implication on the solution that your analysis will compute. What is that implication? What does it imply about your solution? And I was giving away a hint that this has to do with the lattice of solutions that we talked about, I would say maybe a month ago or a little bit less than that. So when you are solving an analysis problem, what kind of solution are you looking for? There is a specific name for that solution. What was it called? So maybe I should draw the lattice of solutions then. So I'll just draw it down here. So the lattice of solutions was as such. Here you have bottom, here you have top. It's monotone. Well, it was the monotone framework, right? But there was a specific name for that solution. So we mentioned that this is probably the actual solution or the actual behavior of the program. But this is not computable because it reduces to the halting problem. So just like everything else with program analysis. So we cannot find that. And then we said, well, we are going to over-approximate that using a certain solution. What was the name of that solution here? I'll give you one more hint. It has to do with an operator that you're seeing right in front of you on the slide. Okay, so let's remember it together now. So, what would that solution be? So how do we actually over-approximate the solution of a program? Well, we said we're going to say, well, I'm going to have the first path, the second path in the program, and the third path, P3. We are going to over-approximate the behavior of each path by saying, this is going to be the composition of all the flow functions along this path. So this is going to give us F1, which is the composition of all the data flow functions of all the statements along this path. The same thing for the composition of all the flow functions along P2. The same thing for all the composition of all the flow functions along P3. Let's call these F1, F2, and F3. And then what do we do for all those function compositions? Yes, it's the MOP solution. It's the meet over all path solution. Right? This is the best over approximation that you can get for the actual behavior of the program. The MOP solution. However, we also mentioned that to compute the MOP solution or the meet over all path solution, it is also not possible to compute that for many types of programs and many types of data flow functions. So an over approximation, yet another over approximation of that is, oh, I didn't want to do that. So this is the MOP solution. So we found that, well, another over approximation of that would be the least fixed point solution, or the LFP solution. And then there is the greatest fixed point solution, or the GFP solution. And in between, there are various other types of solutions that depending on the configuration, the precision configuration of the analysis, we can go either way. So the one thing that we said back then about distributivity is, if you guarantee that all your flow functions are distributive, this LFP solution is going to be the MOP solution, which means it's going to be the best possible solution with respect to precision that you can compute. So this is why it is something useful, or it is something desirable to define your flow functions to be distributive. And this is one feature that IFDS would use to be able to get the most precise solution for you. Is that clear to everyone? This was a longer than expected refresher, but I think it was necessary to tie in everything together that we discussed in the course so far, pretty much. Does anyone have any questions about what we just discussed here? All right, a couple of no's and all good. So if you feel that you don't have any questions, just please indicate so, because again, like I said, in a real class, I can tell from just looking at the students, but here that is not the case as before. So I don't have any indication whether I should just stop longer if you have any questions, or should I just move on and go and like move on to another topic in the class. But at least in this instance, it seems that we're all good to go. All right. So now that we have discussed that, this is why we would like our flow functions to be distributive, so that the least fixed point solution, which we have an algorithm to solve intra-procedurally, now we're going to see how we do it inter-procedurally, is going to be the meet over all path solution, the best possible solution, the most precise solution we can compute for our analysis problem. All right, why subset? Subset because we are going to use our join operator is going to be the union. So if you have some facts going from one path, other facts going from another path, the way we're going to merge these paths is going to be through the union operator. So we're going to join subsets of facts together. And this is why it's called subset in its third name of the analysis. So this is what makes up IFDS. It's used in defining the analysis using IFDS, or the IFDS framework allows you to define a large class of analyses. So you can define alias analysis, taint analysis to detect security problems, type state analyses, which we have seen very beginning of the course, to track objects and maybe resource leaks in your program, doing constant propagation and some other potential compiler optimizations, reaching definitions to figure out whether a certain computation is needed in the future or not, and also checking for uninitialized variables, and many more analyses that I just can't list all here. So it covers a large class of program analyses and static analyses that we can define using IFDS. So the main thing about IFDS is that instead of having to solve an analysis problem in the sense that we have discussed with the monotone framework, it reduces the analysis problem into a graph reachability problem. So whenever you want to say, for example, in a taint analysis, well, is this variable p tainted or not? You're going to have a graph that represents the data flow facts, and the goal of the analysis is to figure out whether there's a path from the root of that graph to the point P in that graph. And if there is, then P will be tainted, otherwise it won't be. So instead of having to look up sets or maps or whatever you have it's going to be a graph reachability problem. And we know how to solve that quite well. So how do we define this graph reachability problem? Well, this is the control flow graph, or the exploded supergraph rather. We're going to have right before every statement, and this is important, it's going to be right before every statement, we're going to have a node in the graph that represents the variables that we would like to track in the program. So here we have 0, and we're going to get to that in a second. A, B, and C, these are the variables that we have here. And here we have again another 0, and then D and E. Each node in this graph, in this exploded supergraph, is going to be a fact, meaning that it is true that this variable that this node represents is reachable in the graph, which means whatever analysis query that you're asking or analysis question that you're asking is going to be true for that specific variable. And the fact will hold at a statement whenever it's reachable in the exploded supergraph. So let's have some examples before we go on further of some of the flow functions that will determine the flow or the propagation of data flow facts in IFDS. There is the identity flow function. This is pretty simple. Whatever goes in comes out on the other end. So all your outsets, the outset of S is basically the inset of S. Facts before a statement just flow through the statement after and still are true after the statement. Every fact is reachable if and only if it was previously reachable. Pretty straightforward. Another type of fact is something like this, where you are modeling the assignment of A to B. So here in this case, we're going to say the out of S is going to be the input of S, the input set. Nothing will change there. Union, the fact B is still going. It is going to be reachable if that function F is in S. Otherwise, I'm just going to include S as it is, and I'm not going to include the set B. So this basically means that whatever was true before the statement will still be true, and whatever is, and because of that assignment statement, B will also be true, because A is true. So every fact is reachable if it was previously reachable. B is also reachable if A is reachable. Another fact here says the following. There is a slight difference here between that fact or that flow function and this flow function here. And the difference here is that even though we are trying to model the effect of the same statement, the flow function that we're defining is different. The flow function here says the following. The first case is the same. If A is reachable, B is going to be reachable. The second case says, I'm going to eliminate B from the outset if it is not going to be reachable. So I'm going to eliminate that edge that was there before if it is not going to be reachable. So every fact except B is reachable if it was previously reachable, and for B specifically, because B here is part of an assignment statement, I'm only going to make it reachable if A is reachable, which means I'm going to overwrite whatever I had about B from before. I'm going to forget whatever information I had about B from before. And you're going to see this flow function used quite a bit for taint analysis. This type of flow functions here. The second type, or another type of flow functions, is a kill flow function. You're killing facts, and it's very similar to the previous flow function that we had. So if you want to kill something, you're going to use set elimination. You're going to eliminate some value from the set. And this operator here is the set minus operator. So you have seen this already in the assignments, and you're probably going to see it also in future assignments as well. A typical use of a kill flow function is you have some variable A, you assign it a value secret, then you assign null to it or some other non-secret value. So you want to, at that point, you want to kill the fact that A is reachable in the graph, because if it is reachable, that means it is tainted, but it is not at this statement. So A, according to that flow function, is not reachable even if it was before. So it might be reachable in your program up to a certain point, and after that point, A is not reachable anymore. There is also, as opposed to kill flow function, there is a gen flow function or a generator or a generating fact flow function. And usually those generating fact flow function use the union operator because you're trying to add or generate a new fact to your outset. And this is typically used in either initiating the analysis when there is a secret value in the case of taint analysis, or when you have assignment statements, so you're trying to propagate or generate the fact that because of the assignment statement, some variable will also be tainted. 0, which we're going to see in most of our slides today, I'm going to get to that in a couple of minutes, is called the tautological fact, meaning that this fact is always true regardless of whatever statement. And the reason we have this tautological fact is to bootstrap the analysis, as we're going to see also in the future. And the idea actually of IFDS is that to answer an analysis query, you basically just want to know whether the node that represents the variable you're interested in at the statement you're interested in is reachable from that initial tautological fact or not. If there is a path from that tautological fact to that point, that means that your variable is true. The data flow fact that represents your variable is true. There are also some non-distributive flow functions. The prime example of that is full constant propagation, meaning that you have such an expression here, C equals A plus B, and you want to know whether the result C is going to be constant or not. But we're not going to discuss that in today's lecture though. And we're going to see why. So, any questions about these flow functions or the exploded supergraph or distributivity or anything that we've discussed so far in the class today? Not yet. I like the spirit. There will be more questions in the future. All right then. So let's take, before we have our break, let's take a quick example here from taint analysis. And the reason, by the way, that I have many of the examples in this course from taint analysis is that it is the most commonly used static analysis in security. So it gives you also a flavor of how you can actually apply program analysis to the field of secure software engineering and so on. But many of those examples go beyond just taint analysis, of course, as you'll see from the papers that we're going to discuss in the class and also the projects that you're going to come up with as well. All right, so for this example here, we have a main method. We have a method foo. The main method generates some facts, have some assignment statements, and calls method foo. And the question that we want to answer is, does this password here get printed at that point or not? Is that possible? Does this password leak to that point or not? So this is some of the terminologies that you're going to hear regarding taint analysis. Data leaks, sources. So this is a source. This is a source of private information. This is a sink for private information where it can leak to. And here you're asking, is that a data leak or not? Does the private data can leak to that sink or not? So how do we do that? Well, we're going to build our exploded supergraph. So build the CFG for the main method, build the CFG for the method foo, create your ICFG, connect the call size and returns, and then start creating your exploded supergraph. So create the flow functions. So first we're going to have normal, there are four main types of flow functions in IFDS. There is normal flow functions, and these flow functions are for statements that have nothing to do with method calls or call sites. So like a statement like A, assuming the password is basically just the source or maybe a generator for passwords, not a regular method call. So these are going to be normal flow functions. And at the next statement, because B is assigned the value 0, then we are going to kill B, but still we have normal flow functions. The tautological fact is always true, so it is always propagated forward. The fact that A is reachable is also propagated forward because it is still reachable at that point. Nothing has happened to A. Then at the statement B equals foo of A, we're going to cross a method boundary. So now we're going to have a different type of flow functions around method calls. So the first type of flow function is going to be a call flow function, that simulates or models the propagation of data flow facts from the caller into the callee method, meaning A here is the argument. I'm going to assign that to P, so this is why we have this edge here. Tautological fact goes to the tautological fact, it's always reachable. So now I modeled the one direction of the call flow function. Then within the method, I'm going to still have a normal flow function. So P equals 0 means I'm going to eliminate the edge for P because it's assigned the value 0, so it cannot be reachable. The tautological fact is always reachable, so that goes on. And now I'm returning from P, so before I go on, there is a question here. What is the arrow from 0 to A at the very beginning? This arrow here. This arrow here is there because, thanks for that question, actually I forgot to mention why that arrow is there. So that arrow is there because A after that statement is reachable. And it is not enough to say that A goes to A here, but we should say that if it is going to be reachable, it is going to be tainted because we are assigning it this password. And for it to be tainted, it has to be reachable from the original tautological fact. So I have to connect those two here. It doesn't matter whether it's reachable from the previous node for A or not. I don't care about that one. I care about that it is reachable from the tautological fact because it is tainted after that call to password here. Does that answer your question? Okay, cool. So back to the data flow within the method foo here. So we said that tautological fact is propagated forward. P is eliminated, or that edge is eliminated because P is equal to 0, so we don't need that edge here. Now we are returning from that method foo back to the main method, so we're going to have our second call-related flow function, which is the return flow function. So first we had a flow function for the call flow function. Now we have the return, the other direction. The tautological fact is flowing back to the tautological fact of the main. We are returning P here, so we are returning P to whatever was assigned here from that method call. So this is B, so P flows back to B. And this will model the return side of things. The other type of flow function that is related here, sorry, and then we're going to move on to the remainder of the program, and the remainder of the program is just a statement, the sync. So the sources and the sinks, we don't consider them to be method calls. They're just regular statements that have specific meaning to them. And that's why we're going to have a normal flow function around the sources and the sinks. The remaining flow function that is related to the method call is something called the call to return flow function. And these flow functions will determine how before the call, the facts that are before the call, how they are propagated forward after the call. So yes, because of the call itself, we had call flow functions and return flow functions, but what about those calls here? Sorry, those edges here. Do I propagate them forward or not? And in this case, we're just going to propagate them forward. They're going to be the identity function. And this is typically what the call to return flow functions are. Most of the time, they are identity functions. You just propagate them forward. But you could also use them to do some other things, like if you want to kill certain facts or if you want to generate certain facts. But most of the time, they are identity functions. So now we have 4 types of flow functions. We have normal flow functions for non-call statements and for sources and sinks. We have for call sites, you have call flow functions, return flow functions, and you have also call to return flow functions. And this constitutes all the flow functions that you need to define for your IFDS problem. Like I said, typically the call to return flow functions is usually the identity or the ID function because it doesn't affect the propagation of the data flow facts that much. I'm gonna stop here for a couple of minutes because we are halfway through the class, and when we come back after the break, I'm going to explain to you why all what I just said is not actually how the exploded supergraph is created in practice in a realistic IFDS algorithm, and how actually we do it in realistic and in practice for any analysis framework like SUT or WALA or DUP or other analysis frameworks that are out there. So hang in there for a few minutes. After we come back from the break, I'll let you know how it's actually done in practice and how we actually create that exploded supergraph in practice. Meanwhile, if you have any questions, I'll still be available. So please just ask me on the Zoom chat. Text or voice is fine. It's up to you. We're going to continue in about 4 minutes from now. All right, everyone. Welcome back after the break. Let's continue our discussion then. So right before the break, we were discussing how we can build the exploded supergraph by annotating the edges along the graph with the flow functions. Normal flow functions for non-call statements. For call statements, you have call flow functions, return flow functions, and call to return flow functions. However, the way we just constructed it is a little bit weird and it doesn't seem practical enough. And here's why. So in fact, what we actually do in practice is building it on the fly. So let me first tell you what the on-the-fly construction is, and we're going to go back and see how that differs from the naive way of constructing the graph that I was just discussing. So the on-the-fly ESG construction or exploded supergraph construction is, as we're going through the statements of the method, or the statements along the exploded supergraph, the statements along the ICFG, we're going to construct the ESG as we go. Just like we did with the call graph, if you remember that. The first thing that we're going to do is we are not going to create any nodes or edges unless absolutely necessary. So we're not going to have any nodes or edges that do not lead anywhere. So this will lead to a more sparse ESG that has fewer nodes and fewer edges in there. The first node that we're going to have in our ESG is excuse me. The first node that we're going to have in our ESG is the zero, or the tautological fact, and we're going to have a little initial self loop edge there that will bootstrap the whole analysis just to make that initial node there reachable. Then as we go, we're going to add nodes and edges as needed. So after the first statement, A equals password, A is now reachable because A is tainted, so it has to be reachable on the graph. So we're going to add a node for A, we're going to add an edge from the tautological fact to A, and the tautological fact is always reachable by itself. So this is the normal flow function that we have. Not only that, we're also going, as we go at every single step, we're going to have summary edges that summarizes the data flow so far, so that at the end of our execution of this algorithm, we're going to have a set of summary edges that summarizes the flow from the initial tautological fact up to that point, and it's going to be a matter of consulting that list of summary edges so that we can answer the analysis query. Not even we have to propagate or navigate through the graph, we can just look at the summary edges. Does that edge exist or not? If it exists, then that means that our data flow fact is reachable from the tautological fact or not. So in this drawing here, we're going to have those summary edges as the red edges. Everything else will be in white, in color white. So at the first step, the summary edges are basically pretty much the same as the normal flow edges here. And those summary edges, we're going to call them path edges. But we're going to remove the other edges in the graph so that we can maintain only the path edges as we go, for brevity, of course. Then after this statement, tautological fact is again still reachable. A is also reachable. B is assigned 0. B doesn't, it wasn't even reachable before then, so I don't have any node for it. And now it is assigned 0, so there is no need to add any nodes or edges for B. So I'm just not going to do anything. And then what would I do next? Well, I'm going to create my path edges from the initial tautological fact up to that point. So I'm going to create those two edges here, and I'm going to forego with the other edges in the exploded supergraph. And so far up to that point here in the program, these are going to be my exploded supergraph. I'm going to have 1, 2, 3, 4, 5 edges in my exploded supergraph. And I can pretty much answer any question that you want to ask about taint analysis or taint in this program. So if I want to say, is B tainted at that point? Well, I'm going to look at the edges that I have here. I don't have any edge that goes to B that starts from 0, the tautological fact, so it is not tainted. Is A tainted? Well, if you want to ask that about after the second statement, I have an edge from the initial tautological fact that goes along and goes to A? So yes, it is. So I can answer any question you have about it, about those variables. So every step we're going to extend the path edges further so that we can know from the initial statement in the program or the entry point of the program up to that point whether something is reachable or not. Then we have a call flow function, and that call flow function here is assigning the zero tautological fact to the other zero tautological fact, and A to P, because P is now the parameter of the method foo. Again here, for every method, we are going, the first nodes or the nodes before the first statement will need to have this self-initialization loop so that we can bootstrap those nodes in the graph. So tautological fact will have its self-initialization loop, the same for P, and if we have any other arguments, we're gonna add those self-initial loop to all of them as well. But up to that point, the tautological fact, the zero tautological fact is has its own self-initialization loop. P, this edge here, we basically eliminated because P also has its self-initialization loop and it is not tainted up to that point, so I'm not going to create path edges to it from there. So the only edge that I'm going to extend here after the statement is the edge from 0 to the edge to 0 afterwards. P here, because it's assigned 0, it is very similar to that assignment statement B equals 0, so there are no edges that are going to be created here. So basically what that means is after this statement there are only going to be one path edge for the method foo from the initial 0 fact to the second node that represents the initial 0 fact and there will be nothing else from that method. What is really nice about this is we will consider this to be our method summary. Remember from the functional approach that we discussed in the previous lecture, very briefly at the end? So this path edge here represents this functional method summary, or the summary of that function here. And I'm gonna reuse, or I can reuse that summary at every single other call site in my program. So whenever I have a call to method foo, I'm gonna look up that method summary because I already computed it. And I'll see, well, okay, does that, do I have any edges that I should use or I can use here? Well, there's only one path edge. There's no other path edge here, so I can just say that this method, regardless of what happens or who is calling that method with whatever parameter, it doesn't have any side effects. It doesn't cause any variables to be tainted, or it doesn't remove the taint from any variables. It basically does nothing here. The return flow will just be again from the tautological fact to 0. Remember that we don't have an edge from this P here to B like we did in the previous, that's not even right, to B. This one does not exist anymore because we are only going to extend our path edge forward only to those nodes that are already reachable. So if the node does not exist, we're not going to extend any path edges to it. So this allows us to eliminate the unnecessary generation of nodes and edges in the exploded supergraph. And now our path edge is going to be, well, now I'm returning from that method. So this here is going to be reachable, so I need to extend it further from the initial tautological fact. And this is exactly what I'm doing here. So at every single step, once you're done with the local propagation of the data flow facts, you need to extend your path edges into the caller in this case. Now with the call to return flow functions, here 0 is extended further, so that is already captured by this edge here, so no problem. A here is extended further, is propagated further, so we need another path edge from the tautological fact to A here, which is now going to be represented by these two edges here. And before I move on, there's another question here on the Zoom chat. how would the graph look like if it removed taint? Say if the function call was a equals foo a. Ah, right. So if the function call was a equals foo a, everything will stay the same. However, we are not going to have this call to return flow edge, right? Because in this case, we cannot propagate the fact that a is going to be tainted after this call, which means that we're not going to have this path edge here, because that is not true anymore. But we are still going to have the path edge before the call that goes from the tautological fact to a at this statement and at this statement. This is still true, but this one is not going to be true anymore. Does that answer your question? Okay, cool. All right, sounds good. So extending the path edges will generate those path edges here to tell us that A is still going to be tainted. Tautological fact is always true. So after the last statement, we have normal flow functions. Tautological fact is true. A is again propagated forward. So the new path edges, we're going to say that tautological fact is true and A is true as well here. So this here, I can also say that this here is going to be the method summary of the main method. So if that main method is called from some other function in my whole program, this method summary is what I can represent the method by. This is the summary that says this is how the data is going to be propagated from the initial point of the program, the initial point of that method up to the last statement in that method. And now answering the query that says, answering an analysis query that says like, is A tainted at the end of the method? Well, I'm just going to say at the end of the method, this is this statement. There are two path edges at the end of that method. Is A one of them? Yes, it is one of them, so it is tainted. Is B one of them? No, so B is not tainted. Let's say we have another variable C, is it one of them? No, it is not, so it is not tainted. So now the analysis problem is just reduced now to a lookup basically in that list of path edges, or if you want to be more thorough, it will be just a navigation through the exploded supergraph from the initial tautological fact up to that point in the program. So back to the previous naive way of creating it, remember those red paths were the paths that were created unnecessarily. So we had this here, we had this here, we also had this from P back to B, and we had B going forward. But those edges are never even computed in our case here in the on-the-fly exploded supergraph, which means less work for the analysis to do, less data flow facts, i.e. baggage for the analysis to carry forward and propagate forward unnecessarily, which means the analysis can now scale even further. We can scale it up to larger programs with this reduced computations here. So any questions about the on-the-fly exploded supergraph construction versus the naive way of doing it? This is in fact the on-the-fly way is the way that almost all analysis frameworks do it when you get to see how the algorithm is implemented in these analysis frameworks, like in Soot, like in Wala, like in Dupe, like in Chord, like in any other analysis framework that supports the IFDS. Any questions so far? All right, Sounds good then. So now that we have discussed the main algorithm and how it works to create the exploded supergraph, there are some tidbits about IFDS that I would like to share with you. First is, again, remember field sensitivity when we talked about the monotone framework and the data and the interprocedural data flow analysis algorithm. It comes back to us here as well. So if you remember, field sensitive is distinguishes between accessing different fields over different objects. Field insensitive does not distinguish between accessing different fields on the same object. Field based will distinguish accessing different fields but doesn't care about the object receiver of that field access. So here, field accesses in field based to different fields are different, but on the same, they are not distinguished. They are only distinguished by the class that they belong to. They're distinguished, sorry, by the field that they belong to, but only using the type of the class, not the actual object. Field insensitive, A.F would be the same as A.G, would be the same as A.E, would be the same as A.B, and so on. Field sensitive is the most precise of them all. You treat every field access as different. Here, A.F will be the same as B.F, would be the same as C.F, and so on. Well, I guess A1.F and A2.F and A3.F, given that all the A's are of the same type. So we have how that would actually affect the data flow fact propagation and the creation of the exploded supergraph. Let's see. So if we have a field-based analysis, that means that our domain here of the analysis is going to be local variables, any local variable that we have, union the fields that we have in our program, all the fields that are declared in the program. So if we have this straight line of code here, let's create the exploded supergraph as we go. So first we're going to start with the tautological fact here. So what would happen after the first statement? Assuming that source is a source of private information and sink down here is a potential leak of that private information. What will be the nodes and the edges that I should create after the first statement? Think about it for a minute here. So what does it mean that A is equal to source? Anyone? What does it mean that, what does this imply that A is equal to source? What does this say about A if you're doing a taint analysis here? The taint may flow to A. Great. So if the taint may flow to A, what does that say about A in the exploded supergraph? There is an edge from 0 to A. Exactly. So there will be an edge from 0 to A, which means that A is reachable on the exploded supergraph. So if you want to make A tainted, it has to be reachable in the exploded supergraph. So I'm going to add a node for A. I'm going to connect the edge from 0 to A as such. After the first statement, B is equal to new DS, some class DS. Doesn't do anything about the data flow fact, so I'm not going to generate any facts. A is still reachable at that point. After the second statement, or the third statement, C equals new DS, again, it doesn't change anything about the facts of A, doesn't add anything to the facts of B and C, so no edges generated for them, but A is now reachable as well. Now at this assignment statement, BF equals A, what does this statement say about BF? If at that point A is tainted, what does this say about B dot F? The taint flows from A to B, so there should be an edge from 0 to B. Are you sure about B? Does the taint here flows from A to B or to something else? And why does it flow to B? Ah, that's a very good question. So here we have a question that says the following. If B dot F is tainted, doesn't that mean that B is also tainted? What do you think? Let's have a quick poll here in the class. What do you think? If B dot F is tainted, if an attribute of a class or an object is tainted, does that make the whole object tainted or not? If you think it does, just type in 1. If you think it doesn't, just type in 2, or yes or no, whatever you prefer. If you think that tainting B.F taints B, just say yes. If you think that it doesn't, just say no. I guess yes with a question mark means maybe. What do the others think? It depends on the class. Okay, another maybe. What about the others? I think yes. Okay. So let me give you an example here. What if you have a hash map or a map of some sort and you insert a secret value in this map? Does that make every other value on this map or every other mapping that this map holds also secret? Do you think that would be the case? So if you have a map of some values or some keys to some values and one entry in this map is secret, does that make the rest of the map all secret? No? Okay. Why not? Another no. That's true. So it doesn't make sense to make other values secret, but we don't know which value we will use in the future. So if you're going to draw a value from that map in the future, or get a value from the map in the future, you might get the secret value. So there must be a way for you to distinguish between those values that you're going to retrieve from the map in the future, so that you know that if you are retrieving the secret value, you're going to say, well, I'm retrieving a tainted value. And if you're retrieving a value that is not one of those secret values, then you're going to say you're retrieving a value that is not so secret. So we can treat this object here in a similar way. It's basically, an object is basically holding a map between the field names, which are the keys, basically, in this mapping, to their values, which are the objects that each field represents. And luckily, there is an easy way for us here to know how a specific key represents which specific object, just by name. In a data structure like a map, we might not have this as easy as such, because you might have an arbitrary large number of entries in the map. You don't know, you might add more entries to the map in the future. But at least in most sane languages, you cannot really modify the objects at will there. So you have a specific structure for the class that is not easily changed, and you cannot just say that I can just add fields as they go. I mean, you can do that in a language like JavaScript and other languages, but not in most sane languages anyways. And here we can just say, okay, if f is tainted in our case, I will say b.f is tainted, but I don't necessarily need to say that all b is tainted with all its fields, because what that means is, if you say that f is tainted implies that b.f is also tainted. If that's not what I meant here. If b.f is tainted implies that b is tainted, then that would also imply that b.g is tainted, which implies that b.e is tainted, and all the other entries, which might not be the case. And even though this is a sound over approximation, but it's a really imprecise one. And there's already an easy way for us to distinguish between those field names, so why not make use of that? Yes, exactly. So this is why we specify b.f, b.g, and so on. And remember, we're doing this as field-based analysis. So there is a way for us to distinguish between b.f or b.g or b.e. So here, let's go back to this question here. When we have b.f is equal to a, what would be the value that is tainted? Knowing that a is tainted, is b.f. Great. So I should have an edge, like you're saying here, from 0 to b.f. But remember, we're doing this analysis as field-based, so I don't actually know what b.f is. This abstraction does not exist. Exactly, it should be ds.f. I don't know what b is here in this field axis. To me, as an analysis or as an algorithm, I only see ds.f. And I only see ds.f because ds is the type of b according to this allocation site here. And I don't know what b.f is, but I know ds.f. So instead of having an edge from 0 to b.f, I'm going to have an edge from, not really the 0, but from a, because it is the part that generates the assignment. So I'm going to have an edge from a, again, will be reachable, and I'm going to have an edge from 0 to ds.f, and I'm just skipping through the intermediate edges that I'm computing. So here I'm only showing the path edges just for simplicity. Otherwise, the exposed supergraph will just look weirdly entangled on the slide here. All right, so something is missing in this slide here, and I should fix it, which is that semicolon here. I should fix that soon. I'll fix that before I upload my slides. So now when I go to c.f and it is assigned d, what would happen at this point? So C dot F is the field access in the code, but you always have to remember what your analysis abstraction is, regardless of what the code actually is saying. So in our analysis abstraction that is field-based, what is C dot F? D is tainted because we treat C dot F as DS dot F. Yes, exactly. Because our analysis treats fields or field accesses using field-based analysis. So B dot F is DS dot F. And C dot F is also DS dot F. And I'm going to look up my exposure supergraph and I was like, at this point, DS dot F is reachable. So I am seeing C dot F in my code, which the analysis will see as DS dot F. So D should also be tainted. So now I'm going to have an edge from both the tautological factor itself and from tautological factor DS dot F. So now it is also reachable. And now I'm going to generate a new fact for D to make D also reachable at that point. And now I'm going to signal here to my sink that D is going to be tainted and D is going to be leaked because the analysis thinks that D is going to hold a tainted value or a secret value. So even though that the algorithm is correct, just by you choosing the wrong abstraction for the analysis, in this case field-based abstraction, treating fields in an imprecise way, you might actually get the wrong result. I mean, it's a safe, again, it's by wrong here I don't mean an incorrect result or an inaccurate result. I mean something that is less precise than you're looking for, that's what you're aiming for. It is still a sound over approximation, but it is not what you're looking for. You're just propagating more false positives than necessary, because this is going to be a field-based analysis. If we're using a field-sensitive analysis, on the other hand, where we are differentiating between the accesses of fields and the objects we're using for the access, in this case, our domain is no longer locals union fields. Our domain is all access paths in our program that have a certain local variable as a base of the field access, and then followed by a successive accesses of fields, f1, f2, f3, up to fn, where L is a local variable and Fi's are fields, and n is greater than or equals 0. In this case, we are going to have only b.f, not ds.f, and we are going to correctly, up to that point, assume that up to that point here, say that b.f is going to be tainted, but when we come to that statement here, C.F is not tainted anymore because we have a more precise abstraction that can differentiate between B.F and C.F. So that assignment statement does not say that D is going to be tainted, and I'm not going to generate a fact for D or say that D is tainted after this statement here. Just by changing the analysis configuration, you land on a more precise solution versus a less precise one. We are almost at the end of our lecture. Well, actually, the clock turned to the end of our lecture. So I'm gonna stop here for today. I'm gonna continue with a quick, brief summary of what we have discussed so far in the lecture today on Tuesday, and then I'm gonna continue with IFDS. And if we have time at the end of the lecture, I'm gonna talk about another abstraction above IFDS that allows us to analyze or define certain classes of analyses that we cannot define within IFDS. And hopefully on Thursday next week, we're going to have some time to describe non-distributive analysis problems and perhaps maybe one other topic as well, time dependent. Thank you all for attending the lecture today, and I hope you have a nice long weekend. Make sure that you stay safe, stay healthy, and have some time off. It's important during these times. If you have any questions, feel free to ask me or Ifaz. We're here to help you out. We're here to provide the best learning environment for you. So please reach out if you have any questions about anything in the course. I'll be happy to help out. Thank you, everyone. I'll see you next week.